Hello, some of you may know that I had a bit of diarrhea yesterday. Thanks for your concern. I feel much better today. So today we can move on to the fifth device. It's the diode. The diode has this circuit symbol. It has a triangle kind of like pointing in this direction, and then there's one single line here. An actual diode may look like this. Doesn't look very interesting. This one is a light emitting diode, LED. So when the current passes through this diode, it will light up. The first thing I have to tell you about the diode is the two terminals are not the same. You cannot anyhow switch the two terminals. So this terminal, the base of the triangle, is called the P junction, and the other terminal on this single line side is called the N junction. So the manufacturers of diodes will also have to tell you which is a P junction and which is the N junction. For example, this one here, this bar here actually corresponds to this line. So this is the N junction and this is the P junction. For a LED, usually the longer leg is the P junction. So this is the P junction and this is the N junction. Now some technical lingo here. If you are connecting a diode such that this N has the higher potential and this N has the lower potential, we say that this diode is in forward bias. So conversely, if you are connecting up the diode such that this N is at a higher potential than this N, we say that the diode is in reverse bias. Okay, we can now look at the IV characteristic graph of an ideal diode. Let's start with when the diode is under forward bias. It turns out that when we apply a forward bias on the diode, the IV characteristic graph looks like this. It's a vertical line that starts from the origin. What does this mean? It means the tiniest positive bias can produce an infinitely large current. So maybe this is at 0 volt, maybe this is maybe 0.1 volt, maybe 0.01 volt, maybe 0.0001 volt. So if it's an ideal diode, the slightest forward bias and the diode will be conducting a very large current. How would you describe this resistance? 0 ohm, right? The V to I ratio is 0. Now let's look at when the diode is under reverse bias. Guess what the IV characteristic graph looks like? It's a horizontal line that starts from the origin. So this could be at 0 volt, this could be at negative 1000 volt, negative 2000 volt. No matter how large a negative bias you are applying, if it's in reverse bias, no current can pass through the diode. So how would you describe this resistance? Infinitely large, right? So basically, when a diode is in forward bias, it behaves like a short circuit because it takes practically 0 volt in order to conduct a current of any magnitude. On the other hand, when the diode is under reverse bias, it behaves like an open circuit. So basically, a diode is like a one-way valve. It's a perfect one-way valve. If you try to push current this way, it behaves like a 0 ohm wire. But if you try to push current the other way, then it behaves like an open circuit with infinite resistance. So to analyze the A-level circuits that you'll be encountering is very easy. You just have to decide whether the diode is under forward bias or reverse bias, and then replace them with open or closed circuits accordingly. So for example, in this circuit here, there's a 6 volt battery here. So we are trying to push current this way. So if you're trying to push the current this way in the direction of the triangle, this diode will be under forward bias, which means you can replace it with a 0 ohm wire. So you have 6 volts across this 3 ohm resistor, you get 2 amps flowing through this branch. What about this diode? We are trying to push current this way, which means this diode is under reverse bias. So it behaves like an open circuit. So no current will pass through this branch. Easy, right? So that's an ideal diode. In practice, diodes are not perfect. So when they're under forward bias, instead of that vertical line through the origin, you may get this curved shape here. So how do you describe this resistance? It starts off very large, but the resistance drops quickly, right? So in a practical diode, you need a certain turn-on voltage before the resistance drops rapidly towards 0. What about when it's under reverse bias? So instead of totally no current, you can have a bit of a very small current, and that current is called a leakage current. Going back to the circuit just now, so just now we assumed that they were ideal diodes, right? So if they are not ideal diodes, then for this one, you'll still be under forward bias, so you'll still switch on, but it requires a turn-on voltage. Let's say it requires 0.6 volts before it turns itself on. If that's the case, then we have 6 volt here, and the other end will be at 5.4 volts because it requires 0.6 volts to turn this on. So with 5.4 volts across this 3 ohm resistor, you can calculate the current through this branch to be 1.8 amp. As for the other one, it's under reverse bias, But if it's a practical diode, it may have some leakage current. So instead of zero current, you can have a very tiny leakage current, let's say 1 milliamp. So a very tiny current of 1 milliamp will pass through this 3 ohm resistor, which will make the potential at this point here 3 millivolts. But then this slide is already beyond your A-level syllabus. A-level syllabus is usually about ideal diodes. So you just need to replace this with a short circuit and replace this with an open circuit. Alright, that's all. Ta-ta!